We've been talking an awful lot about various DCS features, menus, options, and all that jazz for quite a while now. Let's take a break from all that digital stuff, change the pace a little, and talk about layout wiring for a few minutes. When you get your own DCS setup and you look in the instruction book, you'll find that it mentions wiring very early in the book because it's a very important part of DCS. The book talks about using 16-gauge wire, star pattern wiring, the use of terminal blocks, and a few other things. Now, I don't often tell someone to ignore the instruction book, but I'm almost going to do that here. I'm going to suggest that before you get into doing any work on your wiring, just hook up the system and see what happens first. There are so many variables in wiring a model train layout that you won't know whether you actually need to do any wiring changes unless you simply hook it up and try it first. You may find that it works just fine with the wiring you already have. However, if it doesn't work properly, you may need to do a little work on your wiring. How will you know if it isn't working right? Well, if it's really bad, you'll see error messages on the remote that say check track or out of RF range, and you won't have complete and reliable control of the trains. However, there may be intermittent dead spots on your railroad that may not show up just by running a train. There are two ways to test the signal strength on your layout: the design engineer's method and the fun way. Let's take a look at the engineer's method first. As you might guess, it's in a menu on the remote. First, place a Proto Sound 2 locomotive on the track and get it running at about 20 miles an hour or so. Then press Menu, scroll to the System menu, press the thumb wheel, and scroll to Track Signal. Scroll to the engine you're running and press the thumb wheel. The LCD will change to this screen, where you will see a number representing the quality of the DCS signal on the track. A perfect signal is a 10, no signal is a 0. The screen will update every second or so, indicating the signal strength. If you have signal strength numbers of 8 to 10 everywhere, you won't have any trouble at all with DCS, and it'll work fine on your layout. If you occasionally see the signal strength drop to 5 or 6, first thing to do is clean the track and try again. Many times that'll get the signal strength up into the 8 to 10 range, but even signal strengths of 5 or 6 will allow the DCS to work just fine. If you see your signal strength drop to 1, 2, or 3 for long periods of time and cleaning the track doesn't help, then you're probably going to have to make some wiring changes. There is another way to test the signal on the track, and it's a little more fun than just watching numbers on the remote. You can use the Protocast feature to put music through the locomotive sound system. Playing music is the most demanding test of the DCS signal because it requires more communication between the TIU and the track than any other DCS function. Here's how to set up and use Protocast. You'll need a small cassette or CD player with a headphone jack. You'll also need a cable with 1/8-inch male stereo plugs on both ends like this. Play the tape or CD and set the volume level at a mid-range. Plug one end of the cable into the headphone jack on the player and the other end into the Protocast plug on the TIU right here. Get the train started and press the number 8 button, also marked Protocast. The regular engine sounds will stop and the sound will change to the music from your player. Listen carefully to the music. If it plays normally everywhere on the layout, you've got good signal strength. However, if the sound cuts out every once in a while, sounds distorted, or you don't hear it much at all, then you've got signal problems and will probably have to do some wiring work. Here again, before you jump in and change a bunch of wires, be sure your track is clean. With DCS, it is very important that the track be clean. If you have clean track, still have low signal numbers, or the music doesn't play well, then you'll need to follow MTH's instructions about wiring to get the signal strength you need. Because there are so many variables in wiring a train layout, There's no possible way that I can show you a surefire fix that I can guarantee will work. What I can do is show you what MTH recommends, explain what star pattern wiring is all about, and make a few recommendations as to the type of wire you should use. There are basically two ways to wire a train layout. Many of you may have used the common ground method of wiring. This is a method that uses a single power bus feeder and a heavy ground wire that runs around the layout. Connections to the track are made from these feeders or bus wires. This method is easy to do, saves a bit on wire because of the single large wire that can be used for the ground or return wire. However, sometimes DCS doesn't work very well with this wiring method. The other way to wire a layout is the method which MTH recommends. There are several names for this method, called star pattern wiring or home run wiring. It works like this. Instead of running a single ground wire and a feeder wire, paired wires for both hot and ground are run from a central point to the track blocks. If you have a large layout, the use of a terminal block can help tremendously. This is the MTH terminal block, part number 50-1014. You place this terminal block in a central location and run a single set of 16-gauge feeder wires from the TIU to the terminal block. This is what is meant by star pattern or home run wiring. Each block of track gets a pair of wires of roughly equal length. This is a much better wiring network for carrying the DCS signal to the track. O-Gauge Railroading's backshop foreman Jim Barrett has tested a lot of different types of wire, and he has found a great wire for use with DCS. It is this, a 16-gauge paired wire with a red and black wire inside a thin blue outer sheath. He has found that this wire does a good job of carrying both the track power and the DCS signal. We are now stocking this wire for sale at O-Gauge Railroading. It's on our website, or you can call our toll-free number to order it. We have it available in 50, 100, and 250-foot lengths. There is another aspect to wiring your layout that becomes important when using command control, and it is a concept called power districts. With command control, you can run more than one train on the same loop of track. In fact, if the loop is long enough, you can run 3 or 4 trains on the same loop. However, if you try to power the entire loop from a single power source, you're asking for problems. Why? Well, let's take a look at the typical power requirements for a lighted passenger train. Depending upon the type of passenger cars you have, the lights in the cars will draw somewhere between 0.2 and 0.4 amps per car. Let's use an average of 0.3 for our calculations. If you have a 10-car train, that means that just the lights in those passenger cars are going to draw 3 amps. What about the engine? Here again, it will depend on the engine and how many motors it has. A 2-motor diesel with a long train climbing a grade can easily draw 3.5 to 4 amps. Add that 4 amps to the 3 amps of power for the lights, and we're at 7 amps for one train. And if you're running 2 powered units with 4 motors, you're going to be somewhere around 10 to 11 amps, the maximum limit for one transformer. If you like to run long, lighted passenger trains, you're going to have a problem if you try to run more than one train at a time if they're both powered from the same transformer. So what can we do about this? After all, one of the main features of command control is supposed to be the ability to run more than one train at a time on the same track. But if we're going to run out of power with a single big train, how can we do it? The answer is to separate the loop into power districts. This power district concept is a fundamental principle of command control in all scales. The idea is to electrically separate a loop or section of tracks into separate power districts and then power each section with its own power source. When you do this, you're spreading the electrical load among several transformers instead of trying to put all the load on one. Here again, this is a fundamental concept of command control, the separation of power distribution among several smaller transformers so that they share the load. And this concept holds true whether you're using DCS or Lionel's Trainmaster command system. Here's how power districts actually work on the layout. Let's say this oval of track represents one of your loops, and you plan to run 2 passenger trains. How do you determine where to divide your layout into power districts? A good rule of thumb is that you need at least 1 more power district than you have trains on the loop. To start, divide the oval into 3 approximately equal sections and power each of them from a different transformer. Let's say we have 2 passenger trains. Each train draws a total of 7 amps. That means it will take 14 amps to run both trains. That's too much power for a single transformer. The Z4000 will trip its circuit breaker at about 12 amps, and each channel on the TIU is rated at 12 amps. By dividing the load among 3 transformers, here's what happens when we run the trains. At the start, we'll assume that train number 1 is in District 1, and that train 2 has the engine and 3 cars in District 3, and the remaining 5 cars in District 2. That means that transformer number 1 has to deliver 7 amps, which is no problem. Transformer number 2, with only 5 cars in it, has to deliver only 2 amps. And transformer number 3 has to deliver 5 amps. Now, let's move each train ahead half a train length and take a look at the power situation there. Now, train number 1 has its engine and the first 3 cars of its train in District 2. So the load on transformer 2 is now up to 5 amps. The rear half of train number 1 is still in power district 1, but with only 5 cars in that district now, the load has dropped from 7 amps to only 2 amps. The second train has moved to a point where the entire train is now in power district 3, so transformer number 3 is now delivering 7 amps. If we move each train ahead another half train length, we'll have this scenario. Train number 1 is now all in District 2, so transformer number 2 has to deliver 7 amps. The head end of train number 2 has moved into District 1. The load on transformer number 1 is increased to 5 amps. The rear 5 cars of train number 2 are still in District 3, so the load on transformer 3 has dropped to only 2 amps. Notice that as the trains move around the layout, the load is constantly shifted to different transformers as the trains enter and leave the different power districts. So even though we're running 2 trains with a total of 14 amps, no single transformer ever had to deliver more than 7 amps. That is the fundamental advantage of using power districts, the ability to use several smaller transformers to share the load instead of trying to power the entire layout with one monster transformer that would exceed safe power ratings for our trains.